In the early part of the 19th century, chemists began to discover organic compounds with chemical properties quite distinct from the alkanes, alkenes, and alkynes. They called these substances aromatic compounds because many of the first examples were isolated from the pleasant-smelling resins of tropical trees. The carbon-hydrogen ratio of these compounds suggested a very high degree of unsaturation, similar to the alkenes and alkynes. Imagine, then, how puzzled these early organic chemists must have been when they discovered that these compounds do not undergo the kinds of addition reactions common to the alkenes and alkynes. So what that means is if they took an alkene, like ethylene, and they added bromine to that, they would end up forming the dibromide that I've drawn here. But if they took benzene, so I'll draw the bond line structure of benzene, and they tried the same thing, what they found is that they got no reaction. And they said, well, that's kind of interesting, because benzene does have these double bonds, which look like the same kind of double bond you would see in an alkene, but it doesn't react, so that's kind of interesting. We no longer define aromatic compounds as those having a pleasant aroma. In fact, many have no odor whatsoever. We now recognize aromatic hydrocarbons as those that exhibit a much higher degree of chemical stability than their chemical composition would predict. The most common group of aromatic compounds is based on the six-membered aromatic ring, the benzene ring. The structure of the benzene ring can be represented in a variety of ways. So even though benzene, which is the most common of all aromatic compounds, and I'll draw the bond line structure down here, even though benzene does have double bonds like are found in an alkene, it doesn't react like an alkene. In fact, it is a very stable molecule. So the benzene molecule consists of 6 carbon atoms. Each one is joined together in a planar hexagonal arrangement, and each carbon is bound to one hydrogen atom. And so if we want to draw the full Lewis structure showing all of the carbons, we have 6 carbons all joined together in a ring, and then we have double bonds that alternate. So we go double, single, and each one of these carbons has one hydrogen attached, like this. But of course, it's much easier to just write the bond line structure like this with our double bonds, and we can also write it like this, where we represent all of those double bonds with a circle like this. So again, the benzene ring consists of 6 carbon atoms that are joined together in a planar hexagonal arrangement. Each carbon atom is bound to one hydrogen. Friedrich Kekulé offered up a model for the structure of benzene in 1865. He proposed that single and double bonds alternated around the ring. We call this a conjugated system. So whenever we have a system of bonds that alternates from double to single, we call that a conjugated system. To explain why benzene didn't react with bromine, he suggested that the double and single bonds shift positions rapidly. The most accurate way to represent the benzene molecules is a resonance hybrid, which is shown using this resonance arrow here. The current model of the structure of benzene is based on the idea of overlapping orbitals. Each carbon is bonded to 2 others by sharing a pair of electrons. Each carbon atom also shares a pair of electrons with a hydrogen atom. The remaining 6 electrons are located in p orbitals that are perpendicular to the plane of the ring. These p orbitals overlap laterally to form a cloud of electrons above and below the ring. Because of the cloud of electrons above and below the ring, there is an even charge distribution over the entire molecule. This allows benzene to exist as a flat, planar molecule. There are several ways that we can represent the structure of benzene. This is the complete Lewis structure here. I like to use this one the most, where I show the 6 carbons in the hexagonal arrangement, but I show all of the pi bonds explicitly. This one, D here, this is kind of a shorthand version, and the circle in the middle is used to represent what is shown in this slide here. which shows that the real benzene molecule is a hybrid with each resonance structure contributing to the true structure. Let's talk about the IUPAC names of benzenes. It says here that most simple aromatic compounds are named as derivatives of benzene. For monosubstituted benzenes, or benzenes that only have one substituent, we name the group and then we just add the word benzene. And this is a great time for me to introduce you to a brand new functional group that we call the nitro group. And that's when we have NO2 like this, so this is called a nitro functional group. And so since this benzene molecule here has a nitro attached to it, we would call it nitrobenzene. This group up here might be a little bit more familiar to you, the ethyl group. And so in order to name this molecule, we simply call it ethylbenzene. And then if we have a bromine attached to our benzene, we would call that bromobenzene. Right? What if we had an iodine attached to our benzene molecule? What would that be called? Of course, it would be called iodobenzene. But things can never be that easy, and you have to know also what is known as historical nomenclature. It says here that some members of the benzene family have unique names that were acquired before the IUPAC system was adopted and that are still frequently used today. So this molecule that you see here on the far left, you have a methyl group attached to your benzene. So it might be a knee-jerk reaction to call that methylbenzene, and technically that could be an acceptable name, but the name that is commonly used, that it was given to this molecule a long time ago, is called toluene, and you have to have that name memorized. And so instead of calling it methylbenzene, we call it toluene. If I have a hydroxyl or an alcohol directly attached to my benzene ring, I call this phenol. If I have an amino group attached to my benzene ring, I call this aniline. And if I have a carboxylic acid directly attached to my benzene ring, I get a carboxylic acid that is called benzoic acid. This condensed structure that is shown here is just another way of writing out the whole carboxylic acid group. Okay, so what I'm drawing here is the exact same thing as benzoic acid. If we want to name a disubstituted benzene, so a benzene that has more than one substituent, we're going to name the groups in alphabetical order. The first named group is at position 1. If a special group, meaning the methyl in toluene or the hydroxyl in phenol, is present, it must be the number 1 on the ring. So that means you've always got to be on the lookout for toluene, phenol, aniline, and benzoic acid. There's also an older system of naming disubstituted benzenes, which uses these prefixes in the nomenclature. So we use the prefix ortho, and that means the substituents are at carbons 1 and 2. Let me show you what I mean. So if I have a substituent at 1 and another substituent at 2, I call this ortho. If I have a substituent at carbon 1 and another one at carbon 3, so we'll just write it like this. This is called meta substitution. And then finally, if I have one at the 1 position and the other one at the 4 position, let me just draw it like this. So I'll put my X over here, my Y like this. We call this para substitution. And so let's take a look at these molecules. I have the 1,2 disubstituted benzene orthoisomer that I could call ortho diethylbenzene, right? Because I have 2 ethyl groups, so this would be ortho diethylbenzene. Or you can simply shorten the ortho. So if you don't feel like writing RTHO, you can just write O like this. That's totally fine. So you could call it O-diethylbenzene, as is shown here, or you could call it 1,2 diethylbenzene. We use the same rationale for the 1,3 disubstituted benzene or the meta isomer. We could call it meta-diethylbenzene. We can simplify meta to just the letter M. We could call it M-diethylbenzene, which of course does represent meta-diethylbenzene, or we could call it 1,3 diethylbenzene. And then finally, if you don't feel like writing out the whole word para, you can shorten that to P. So we can have para-diethylbenzene, P-diethylbenzene, which again represents para-diethylbenzene, or 1,4 diethylbenzene. Let's try naming some polysubstituted benzenes using the following rules. So first, we're going to give the lowest possible numbers to the substituents around the ring. Next, we're going to alphabetize the substituent names. So of course, chloro would come before ethyl, and ethyl would come before propyl, so on and so forth. Then, when the substituents are part of common roots, and the common roots would be things like toluene, aniline, phenol, or benzoic acid, what we're going to do then is we're going to name the molecule as a derivative of that monosubstituted benzene. Again, toluene, phenol, aniline, or benzoic acid. And then we're going to put the common root substituent at C1, but omit 1 from the name. So what that means is if, say, you had, a phenol, so let's say you had a phenol that had, 2 methyl groups on it, you would assume the common root substituent, which for phenol is the hydroxyl, you would assume that's at carbon 1, and then you would have carbon 2, 3, 4, 5, 6, like this. So this compound would be 2,6-dimethylphenol. Let's get some more practice. And we'll start by looking at this tri-substituted molecule, and you can see that the numbering has already been done for us, and that the numbering has been done in such a way to assign the lowest possible set of numbers. Maybe you would think, okay, well, I could start numbering with the chlorine, 1, 2, 3, 4, like this. Well, then the numbering would be 1, 3, and 4, as opposed to 1, 2, and 4. And we always look for the first point of difference, and since 2 is lower than 3, the way the molecule has been numbered with the black numbers is the correct numbering system. And so the numbers that are shown here in black are the correct way to number this molecule. Next, we're going to alphabetize the names of the substituents. Of course, our parent in this case is benzene, but on carbon 1 we have an ethyl, so that's a 1-ethyl. On carbon 2 we have a propyl, so that's a 2-propyl. And on carbon 4 we have a 4-chloro. Now we alphabetize them. C is going to come first, then E, then P. So our molecule will be 4-chloro, 1-ethyl, 2-propylbenzene. This molecule is a tri-substituted benzene, but it has a common root, and that common root is aniline. You must have the structure of aniline memorized. Just to refresh your memory, I'll put it up here. So draw my benzene and put an amino group on here. So you can see that what's boxed in here in the beige rectangle is aniline. So we're going to name this as a derivative of aniline. And of course, I assume the carbon that has the amino group attached to it in my aniline molecule is carbon 1. Then I'm going to number this molecule counterclockwise because that would give this carbon the number 2. And then I'm going to number the molecule going counterclockwise from carbon 1. And the reason why is because then I give this chlorine the number 2. If I had gone clockwise, then I would end up giving this chlorine the number 3. And since 2 is lower than 3, you can see the numbers that are in black are the correct way to number this molecule. And so let's put it all together. I have a chlorine at carbons 2 and 5, so this is a 2,5-dichloroaniline. In IUPAC nomenclature, the group derived from removing one hydrogen from benzene is called a phenyl group. An aromatic hydrocarbon attached to a long aliphatic group is named as a phenyl-substituted hydrocarbon. Notice there's a big difference between the names. Phenyl is when benzene is a substituent or a phenyl group, and phenol is this molecule here, which is also a functional group. And so how would I name this molecule that's shown down here? Well, since it's an alkene, I find the longest carbon chain that contains that double bond, and I want to give that double bond the lowest possible number. So I'll number my butene chain like this. So this molecule is a 1-butene, and since I have benzene as a substituent, and again, when benzene is a substituent, it's called phenyl, This molecule would be called 3-phenyl-1-butene. The polynuclear aromatic hydrocarbons, or PAHs, are composed of two or more aromatic rings joined together. Many of them have been shown to be carcinogenic. That means that they cause cancer. Naphthalene has a distinctive aroma. It has been frequently used as mothballs and may cause hemolytic anemia, a condition causing the breakdown of red blood cells in humans, but has not been associated with human or animal cancers. Anthracene, derived from coal tar, is the parent compound of many dyes and pigments. Phenanthrene is common in the environment, although there is no industrial use of the compound. It is a product of the incomplete combustion of fossil fuels and wood. Although anthracene is a suspected carcinogen, phenanthrene has not been shown to be one. Benzopyrene is found in tobacco smoke, smokestack effluents, charcoal grilled meat, and automobile exhaust. It is one of the most potent carcinogens known. As we have noted, benzene does not readily undergo addition reactions as the alkenes and alkynes do. The typical reactions of benzene are called substitution reactions, in which a hydrogen atom is replaced by another atom or a group of atoms. Unlike addition reactions of alkenes, no carbon-carbon bonds are broken. In substitution reactions of benzene, the carbon-hydrogen bond is broken and the hydrogen is replaced or substituted with another atom or a group of atoms. The substitution reactions we're going to look at are halogenation, nitration, and sulfonation. Benzene can react by substitution with chlorine or bromine. These reactions require either iron or an iron halide as a catalyst. For example, benzene will react with bromine in the presence of iron 3 bromide to give you bromobenzene plus hydrogen bromide. And you can see what's happening here is that we're substituting this hydrogen, and I'm drawing it here at an angle because of the plus sign, we're substituting that hydrogen with a bromine atom. What happens to that hydrogen atom? The hydrogen atom is going to combine with the other atom of bromine to give you HBr. Benzene can also undergo nitration with concentrated nitric acid dissolved in concentrated sulfuric acid. This reaction requires temperatures in the range of 50 to 55 degrees Celsius. So we take our benzene, we treat it with nitric acid in concentrated sulfuric acid, we warm it up, and we end up with nitrobenzene. Remember, you're responsible for knowing the nitro functional group, the NO2. In this reaction, not only do we replace a hydrogen with a nitro group, we also end up with water as a byproduct. Benzene can react with sulfur trioxide, SO3, by substitution. Concentrated sulfuric acid is required as the catalyst. Benzene sulfonic acid, a strong acid, is the product. And so you can see here that what's happening is we're substituting this hydrogen with all of this here. And this is called a sulfonic acid. In fact, there's a new functional group for you, a sulfonic acid. I'll write it out here. And so we produce benzene sulfonic acid, and we also end up with water as a byproduct.